Example 3, we're examining a seam wall cross-section shown in this figure. It has a constant wall thickness. Okay, it has a constant wall thickness 0.5 inch everywhere. Okay, assume that B1 is 12, B2 is 8, and H is 8 inch. So H is here. So H is not from the bottom to top, it's from the point F to point B. Okay, H equals BF, that is 8 inch. Okay, so if the shear force acting on the cross section is V, that's 2,100 pounds, so directed in the negative y direction. So determine the shear flow at the shear flow. Okay, not shear stress this time. We're determining only shear flow at point B, point C, and point F. Okay, of course, the first step we're determining the V, where the V has been given, and then the second step we're calculating the centroid. We're finding the centroid and the I values of them. So we already determined. We calculated that the centroid is 4.83 from inch from the bottom. Okay, so here from the bottom to the centroid, here is y bar equals 4.83 inch. And I is 173 inch to the fourth. Okay, so first of all, let's look at point B. So point B is here. Okay, at point B, so we need to calculate the Q values at point B, right? Since V has been known and the I has been calculated, so we only need the Q. Okay, so what is the QB? QB, okay, we need to cut the area. Okay, so here to calculate the shear flow at point B, we just cut it from here. Right, we got this area. Okay, the area, obviously that is the thickness that is 0.5 times half of AD. Right, AD is just B1, that is 12. Right, so 12 over 2. And this is the area. And the D value is D value, we need to find the centroid first. Centroid here. So what is the centroid? What is the distance from the centroid to the bottom? To the bottom. So what is this value? If we know this value, we subtract the y bar from this value, so we got the D, right? So here this distance will be this H, right? BF or H plus half of the thickness on the bottom, right? T over 2. So this is this distance, since H equals BF, right? So H is 8 plus T over 2 is 0.25. So here is 8.25. Okay, so the D value will be 8.25 minus y bar. Right? Y bar is 4.83. So that is 3.42. Okay, 3.42. Okay, this QB can just be calculated as 10.26. Then the QB, the shear flow, okay, at point B, can thus be calculated as VQB over I. Okay, no T this time, since we're only calculating the shear flow. V is 2,100 times 10.26 over I, so 173. So we will get 124.5. Okay, so here's the unit. Okay, the unit here you have pound and cubic inch. Here's the inch to the fourth. So the unit of the shear flow will be pound per inch. Okay. Then we will examine the other point, the second point, point C. Okay. Point C is the centroid. Okay. At point C, again, we just need to find the QC. Right? We need to find QC. But let's draw this cross section again here. Okay, this is the cross section, and your point C here. So we just cut the area. We cut this half of the area. Okay, we cut the area below the centroid. Then we have know that the y bar is 4.83. And here the thickness is 0.5. That this distance from here to the centroid will be 4.33. Right. Then we can cut it. We can cut it from here to get our area 1 and area 2. Okay. Then the QC can that be calculated by A1 D1 plus A2 D2. Right, so A1 is obviously B2 times the thickness. Right, the B2 is 8. Thickness 0.5 times D1. D1 would be y bar 4.83 minus half of the thickness. Right? And then A2 would be 4.33 times thickness 0.5 times D2. D2 would be half of the height of area 2. Okay, that is 4.33 over 2. Okay, then here we got the result of QC, and that is 23 cubic inch. So the shear flow at point C can be calculated as VQC over I. That is 2,100 times 23 over 173. You get 279. Okay, again, it's pound per inch. Then as your exercise, you can try to use the top half. Okay, the other half you use this half to do the calculation. Okay, you cut it in the middle and use this magenta area to do this calculation and to examine if you can get the same result. Okay, so this is your own exercise after the class. Okay, just try to do this by yourself. Examine if you can get 279 pounds per inch. If you cannot get the same result, meaning that you need to do more exercise to get it right. Okay. Then the last point, the point F. Okay. At point F, we again redraw this shape. Point F is here. So similar to point B, you can cut the area in such a manner. So here the QF is relatively easy to calculate. The QF will be just A times D. Right? So A will be thickness by half of B2. Right? 0.5 times half of B2, 8/2. This is A. And the D will be, again, the Y bar, 4.83 minus half of the thickness. Okay, here you got a 9.16 cubic inch. And the QF, shear flow at point F, will be VQF over I. That is 2,100 times 9.16 over 173. So you get 111.2 pound per inch. Okay, so again, as your own exercise, you can try to do another thing. That is to cut it from here. Okay, I know some of you may really want to do this. Okay, since we cut it in this way, so you can also try to cut it here and to use this area to do the calculation. Here you will get a slightly different result. Okay, you will get a slightly different result. Since what we did here, you're calculating the QF along the horizontal direction. And if you cut it, you cut the green area, so you are calculating the shear flow in the vertical direction. Okay, these are the shear flows in different directions. But since they're at the same point, you can do a comparison. In this current calculation, we did some approximation. Actually, we ignored the connection between the bottom flange and the web. If you ignore the web, so the result could be a little larger. So you can try to do the other calculation using the green area to see if you can get a result slightly larger than this QF we just determined. Okay, but no matter how, if you get a slightly larger one or the same value, it doesn't matter, since if you calculate the stress, the shear stress, in using this number, you will over the t value. The t value will be very small. That is only 0.5. Right? If you use the value calculated from the green area, so you need to use the B2 as the t value. So it will be 8. It will be 16 times larger than the thickness t. Okay, so the shear stress will be much smaller.